In this video, we're going to begin Chapter 7 and start to look at kinetic energy and how it relates to work. So first, we're going to look at kinetic energy specifically, and we're going to apply the relationship between a particle's kinetic energy, mass, and speed, and identify that kinetic energy is, in fact, a scalar quantity. A lot of this is going to be a review of AP Physics 1. So first off, energy is required for any sort of motion. And a few facts about energy. Energy is a scalar quantity, and it's assigned to an object or a system of objects, and it can be changed from one form to another. We know from our previous physics course that there are many different forms of energy, and we transfer those energies from one form to another. And the important part is that in a closed system, energy is conserved, and that means that the total energy of the system at the beginning, all types of mechanical energy, it stays the same. So the total stays the same. We can just transfer between the different types. In this chapter, in Chapter 7, we're going to specifically focus on kinetic energy. Now we'll look at work being done by a few different things, but we're going to focus on kinetic energy and how it relates to work. And then in Chapter 8, we'll get into the other types of energy. We're also going to discuss one method of transferring that energy, and that's through the idea of work. So kinetic energy, basically, we know that the faster an object moves, the greater the kinetic energy it has. And kinetic energy is 0 for a stationary object. And so we can quantify this using an equation that K is equal to 1/2 mv squared. Now, this may be a little different in that AP Physics 1 we could have used KE. Well, we're going to shorten things to just use K as the representation of our kinetic energy. And remember, there is no vector sign here because it's not vector, it is a scalar quantity. And the unit of kinetic energy is a joule, and we know that 1 joule is 1 kilogram meter squared per second squared. So let's move into looking at how work and kinetic energy are related. And in section 2, we're going to apply the relationship between force and the work done on a particle. And then we're going to calculate the work by taking the dot product. And so remember how we treated vectors back in chapter 3 with dot products and cross products. Now we're going to start to need to use the dot product of two vectors because we're going to define work using the dot product. And then if multiple forces act on a particle, we're going to calculate the net work done by them and apply the work kinetic energy theorem to relate the work done by a force. And so to account for changes in kinetic energy, we do this by saying that energy has to be transferred to or from the object. So either energy is being transferred into the object or being taken out of the object. And in a transfer of energy via a force, work is done on the object by the force. And so this is an important thought here. Work, which we're going to use W to signify work, is energy transferred to or from an object by means of a force acting on the object. And so energy transferred to the object is positive work. If we increase the energy of the object, that is positive work. And if energy is transferred from the object, then we consider that to be negative work. There are a few misconceptions of what work is because we use the word work in our everyday life and we use it with a non-physics definition sometimes. And so remember, to do work on an object, energy must be transferred. So an example, throwing a baseball does work. We're transferring energy into the baseball. The baseball now has more energy because we exerted a force over distance, and so work is done. However, pushing an immovable object like a wall does not do work because there is no transfer in energy. And we may think that, well, you're expending energy by pushing on the wall, which that's true, but you're not doing any work on the wall because there's no energy being transferred into that object. And so if we start looking at this with our force equation that we had back in last unit, and if we're just looking one dimension, keep in mind, the force we know is equal to the mass times acceleration. That's the net force in that one direction. And we also know that we have this kinematic equation here that we can use where the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times d, the displacement, or if you want delta x there, that's fine either way. And so if we rearrange these using these two equations and we rearrange them into kinetic energies, knowing that kinetic energy is 1/2 mv squared, well, we get the fact that the difference between 1/2 mv squared of our final velocity minus 1/2 mv squared, our initial velocity, that has to equal the force times the displacement. And this is our working definition of work. And so the left side is the change in energy, whereas the right side is work. And so we know work is equal to our force times displacement. Now keep in mind, what approximation do we do here? What simplification did we do in this method? Well, it was all in one dimension. So what if we want to take it into 2 or 3 dimensions? Well, in order to calculate work, the force on an object that is doing the work has to be in the same direction as the displacement. So we only use the component of the force that is along the object's displacement. And so in AP Physics 1, we just changed this vector using our trig triangle, and we took the force vector in the direction of the displacement, and that typically ended up saying that, well, work is equal to FD cosine theta, or in this case cosine phi, if phi is the angle between the force and displacement. Well, that is true, and that works in two-dimensional motion where we have the angle between the two vectors. However, if we want to back up and make this even simpler to state, but maybe a little harder to carry out depending on the situation, but then it can apply to more difficult situations, we write this as a vector equation. And this is the first vector equation that we have here. And so this is where we really start to deviate from the way we treated things in AP Physics 1. And so we define the work as the dot product of the force vector and the displacement vector. Now keep in mind, this is a dot product. This symbol here does not mean multiplication. It means the dot product because these are two vectors. So we have to go back to our dot product techniques, and we can do this. Now, if we have the magnitudes and the angle between them, well then, yeah, we can use FD cosine phi. But if we have the vectors in vector components, we have to carry out their dot product. So a few notes on these equations. Force is constant. Now, if force isn't constant, we'll get into that later, then we have to use some integration techniques if force varies with the displacement or say it varies with time. But for right now, we'll say it's constant. And also, objects are rigid and they act like particles. Okay, so we're not going to take into account any deformation of the object when the force is applied. And we consider work to either be positive or negative. So let's look at this diagram here, and we see that, well, if we have an object, and let's say this object is this bead, and we're exerting a force up at an angle, well, the bead is constrained to the wire, so its displacement can only be along the wire. And so this force acting at an angle, this vertical component does not matter. And so only the horizontal component of the force actually does work on the bead. And so the change in kinetic energy that we experience for the bead is going to be equal to the force times the displacement times the cosine of that angle between. Because we have these two vectors, we have the force vector and the displacement vector, then we can just multiply those times the cosine of the angle. Also, work has the SI units of joules. This is the same as energy, and if we were to use the British system, then the unit would be foot-pounds. Key note here is that a force does positive work when it has a vector component in the same direction as the displacement. So they have to be in the same direction. It does negative work if there is a vector component in the opposite direction of the displacement. And it does zero work when it has no such vector component, such as when things are perpendicular. If we have a force that is perpendicular to the displacement and there is no component in the direction of the displacement, then there is zero work being done. For two or more forces, the net work is the sum of the works done by all the individual forces. So we can either find the work by each individual force and add those together, or we can choose a different method and we can calculate the net force, add all the forces together to one vector sum, and then multiply that by its displacement. Keeping in mind that we also need to just take the component of that is in the direction of the displacement. And so this was kind of stated earlier, but just to recall back the work kinetic energy theorem, that states that the change in kinetic energy is equal to the net work done on the object. So our final kinetic energy minus our initial kinetic energy, that equals the work. And another way we can write this is that our final kinetic energy is equal to our initial plus the work done. Now the key here is we have to keep in mind this net work, is that positive or negative? Are we increasing our energy or are we decreasing our energy? And we can find this through our vector dot product. It'll come out positive or negative. But we also want to use our intuition here and examine the situation and look at, is my force in the direction of my displacement? Or is there a component of my force in the direction of the displacement? Or is the component in that dimension going in the opposite direction, therefore making it negative? So you have to ask yourself those questions to understand, is the net work positive or negative? Some examples here, let's say we have an object, particle that has 5 joules of kinetic energy at the start, and we transferred 2 joules of energy to the particle, so we're doing positive work. Well, then our final kinetic energy is 7, and if we transfer 2 joules from the particle doing negative work, then our final kinetic energy is 3. So that's just simple arithmetic, adding or subtracting based upon whether it's positive or negative work. So let's say we have a particle that moves along an x-axis, and does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes in these different situations? So in part A, we're changing from -3 to -2. B, we're changing from -2 to 2. And C, in each situation, is the work done on the particle positive, negative, or 0? So to answer this, we need to examine the energy. So we have to look at, well, what does the energy have initially and in the end? So looking at the energy, and you might just immediately say, oh, we're going from -3 meters per second to -2 meters per second, so we're increasing by 1. Well, let's hold off on that. Let's just look at, well, what is our energy here and what is our energy here? Well, our energy initially, using 1/2 mv squared, we would have 1/2 times the mass, which we don't know what the mass is, but that doesn't matter, times -3 squared, which would give us 9. So we'd have 9 halves times n. Whereas when we're moving -2, well, then we are going to have 4 halves, or just 2m. So we actually decrease our energy here. And a way that you can depict this object is moving to the left. And so if it's moving to the left at 3 meters per second, and then now it's moving to the left at 2 meters per second, well, there had to be a force to the right. Well, if it's moving to the left and our force is to the right, these are in opposite directions, so negative work has to be done in this situation. So we're decreasing our energy, negative work has to be done. Now let's look at B. We're changing our direction here. So we have acceleration, and we know if there's acceleration, there has to be a force. But let's keep in mind here, what is the work that is being done? Well, let's look at the change in energy. So if we change from -2 meters per second to +2 meters per second, we have the same kinetic energy. So since our energy remains the same, we have to have 0 net work done on the object. Now, keep in mind, that doesn't mean that there isn't a force that is doing work. And so, yeah, in order to change the direction, there has to be a force exerted on this object to change its direction and to change the magnitude of its velocity. However, to change it from -2 to 0, it's doing negative work because the force is going to be pushing to the right as this is moving to the left. And then that negative work amount, Well, it's also going to go from 0 to 2, and that work is going to be positive. And so the net work on the object is 0 because the negative work and the positive work have the same magnitude. When you add those together, you get 0. So just because there's 0 net work doesn't mean there aren't forces doing work, or it doesn't mean there aren't forces acting on the object. It just means all the forces added together give you a net work of 0. Finally, in this video, we're going to look at work done by a gravitational force. And so we're going to be able to calculate the work done by a gravitational force when an object is being lifted or lowered. And we're going to apply the work kinetic energy theorem to situations where an object is either lifted or lowered. And so we calculate the work as we would with any other force. So if we're looking at a gravitational force, we're going to calculate the work the same way. It's just the difference here. We know that our gravitational force is going to be the mass times baby g. So the work done by gravity, that's why we have work subscript g, is going to equal mg times the displacement times cosine of the angle between them. So by doing that, looking at an object that is rising, so an object that is rising in the air, the work done by gravity. Now keep in mind, this is the work done by gravity, not the net work on the object. Okay, so we're only looking at displacements going up, so the work done by gravity is going to be a negative mg times the displacement. Whereas for an object that's falling, well, then the angle between the force and the displacement will be 0, so that means we'll get a positive mg times the displacement. So this means that the work done in lifting or lowering an object while applying an upward force. So if we're applying a force to the object, gravity is also applying a force, then the change in kinetic energy, which is the final minus the initial, is going to equal the work done by the force that we apply plus the work done by gravity. So for a stationary object, that means the kinetic energy is not changing, and so the kinetic energies are 0. So therefore, we see that the force applied, the work done by the force applied, has to equal the negative of the work done by gravity. Since they're in opposite directions, they are doing opposite work, and they have to have the same magnitude because the net force has to be 0. So in other words, we can say that the force applied in lifting something is equal to the negative of mg times the displacement times the cosine of the angle between them. And this applies regardless of path. And this is one of the nice things with work done by gravitational force or work done by lifting or lowering an object. We don't care about the path. We're only looking at the displacement or in other words, our vertical displacement. We're looking for the displacement in the vertical direction. And so looking at this diagram here, we see that the orientation of the forces and their associated works for upward and downward displacement. And so we do positive work when we are moving upward, and the positive force, the upward force, is doing positive work when the object is being raised up. Whereas if it's being lowered, then it does negative work. And the gravitational force is the opposite. And so keep in mind here, these forces don't have to be, I should say the works don't have to be equal. They are only equal if their kinetic energies don't change. So if the kinetic energy is changing, then we are going to have an imbalance in the work done because there has to be some net work. And if the works are unequal, you will need to know the difference between the initial and final kinetic energies to solve for the work. So let's look at a couple other examples here. And say you're a passenger on this sleigh and you're being pulled up a ski slope. And so the tension does positive work because it's in the direction of your displacement, whereas gravity does negative work because you are being raised up. Gravity is down. And if you're in an elevator and you're being lowered down in an elevator, the tension is doing negative work because that is directed up and you're moving down, and gravity is doing positive work.